In the previous sets of slides, we looked at sampling. And most of the probability problems that we worked in Econ 3402, you pick an individual out of the population at random, and you assume that the mean and standard deviation are associated with a normal distribution, and you convert information about that individual to a standard normal distribution. You get a z-score, you look up a probability in the z-table from that z-score. And so that is for one person out of a population, but we can also do this with samples. And samples are independently drawn collections of observations of a quantitative variable. Where this really comes into play in Econ 3402 and Econ 3406 is differences between the population and the samples, and differences between probabilities associated with drawing one person out of a population compared to drawing a sample of size n out of a population. So the normal distribution associated with any particular population, hey, there's a mean mu, there's a standard deviation sigma. With a sample from that population, there's a different normal distribution, and we call this the sampling distribution. So when I take more than one person out of the population and examine averages of those samples, those averages behave differently than just taking that one person. So there's a different distribution for sample averages compared to just individuals. And we have the same mean, but samples are not as dispersed from the mean as individuals. And just to think of the logic behind this, let's say you take two individuals out of a population randomly. There's a 50% chance that either person will be above the mean. There's a 50% chance of being below. And if you think about it, if you take two individuals, there's a 50% chance that one will be above and the other will be below. And there's also a 50% chance that they'll be on the same side of the mean, either above or below. So all of this is to say that when we examine averages, oftentimes we'll get individuals that are above the mean averaged with individuals that are below the mean. But what this serves from a practical perspective is what this does is pushes those sample averages closer to the mean. So if we take some people above and some people below, we'll get something that's kind of in the middle. This is a hallmark feature of the sampling distribution. So I always like to think of it in terms of randomly selecting people on height. You may have some taller people, some people who aren't as tall. If we look at just taking one person out randomly, we may have a fairly high percentage chance of taking someone who is tall. But if we average a few people together, the probability that that average is also of a taller person is not as high. This is a key insight for statistics. So what we end up doing is we take a lot of samples, we average them together to get a sample mean, but the sample mean is fairly close to the true population mean. And we use this logic repeatedly when we consider confidence intervals. So let me give you an example. Let's go back to the example we had about cooking dinner. Remember, the mean time to cook dinner was 50 minutes with a standard deviation of 15. And let's say I want to look at the probability of 9 randomly selected dinners averaging to a cooking time of over 60 minutes. So I have 9 dinners that I pick randomly. I don't just pick based on my being slow. I just pick them the next 9 dinners that I make without regard to time. Well, going back to these previous slides, we know that the probability of one dinner being 60 minutes or longer is 0.2514. That's one dinner. But what about 9 averaging to 60 minutes or longer? What does that look like? It's not 25.14%. So to have 9 randomly selected average to that length of time requires me to consistently and randomly be selecting long dinners, which is unlikely. So every time I pick a short dinner, I would have to replace it with a very long dinner, and that just isn't that likely. So what we do in these circumstances is we modify the z-score. We still have x minus the mean in the top, but we modify the standard deviation to have the standard deviation of the sampling distribution. So I take sigma and divide by the square root of n. So sigma is still 15. That's still my standard deviation, but instead of having one meal, when I had one meal, I have 15 divided by 1, which is 15. I get a z-score of 2/3. Now I have 9 meals, so I take the square root of 9, which is 3. So I have 10 in the top, 60 minus 50, but I have 15 divided by 3, which is 5 in the bottom, so I have 10 divided by 5, which is 2. That's a z-score. Now let's say I look that up in my z table. I don't go to 2/3, I go to 2.00. which you can see here, 0.9772, row 2.0, column 0.00. Okay, I subtract that from 1, I get 2.28%. I could use Excel. The only difference that I would have to do is replace the standard deviation of 15, which is per person, or per dinner rather, to 5, which is per sample of 9 dinners. And just to unpack the logic, in order for us to get a sample of 9 meals that average to an hour or more to prepare, we need to consistently, randomly draw long meals out of the distribution, and that is unlikely. So every time I draw a meal randomly that takes less than 60 minutes, you need to replace it with a meal that is at least 60 minutes, but that second thing is fairly unlikely. More generally, I should think that getting a sample of 15 meals to average to an hour or more would be even more unlikely, but 2 would be somewhat more likely. So as n goes up, my samples are more tightly distributed around the mean. And you can see that here in this picture. So let's pretend we want to examine the distribution of the weight of pasta put onto a plate at a restaurant. Okay, this line down here, the flatter line, is the population distribution. Let me just zoom in on that here. Okay, we'll move down. This line right here. The taller line is a sampling distribution of 20 meals in an evening. Note that there may be dispersion among individual plates. You may get a lot more pasta or a lot less pasta, but there will not be as much dispersion for the averages. And you're more likely to get averages close to the mean compared to individual observations. So all I want us to take away from this sampling distribution is that when we have a sample of size n, we need to change the z-score to account for that in some way. And in these previous problems with z-scores, we still have had a sample of size n. It's just been that n is 1, and so it doesn't matter. But now it will. Why do we focus on this sampling distribution in statistics? In principle, it's because we're trying to learn from the samples. So I should be learning something when I sample. And the first thing that we quote unquote learn is what's called a confidence interval. So, the definition of a confidence interval, and this is important, it's a region where if I were to repeatedly sample, I should find the population parameter X% of the time. And to put it like this, I draw a sample from the population, I draw a region around it. The true population mean is either in there or it's not. But if I keep doing this process over time, the process will locate the population mean X% of the time. So, trying to put it in layman's terms, every single time that I sample, all that I know about the population is what I learned from the sample. So if you ask me to describe West Georgia students' feelings about a musical artist, I don't know how they feel about that artist. I have no idea. All I can learn is from the sample. So I gather the responses, I take the average. If I sample differently, I'll get a different sample average. I can pin down plausibly what the true sentiment of West Georgia students is X% of the time if I repeatedly sample. So I know that each sample that I get is different, but if I keep doing this process of sampling, I'll generate regions that will capture the true sentiment X% of the time. And we choose different levels of confidence for our confidence interval. So you can make regions of different sizes. You can be 90% confident, 95% confident, or 99% confident. Those are the three regions we're going to focus on in this class. Those are the three regions that are common in a stats class. So let's take a look at the confidence interval formula. Confidence interval. I take the sample mean. I add and subtract z star. Z star is a critical value. Sigma is the standard deviation. N is the sample size. So this last part of the formula is called the margin of error. I add and subtract the margin of error to my sample mean. So from a practical perspective, you take a sample, it's probably not the true population mean, so you give yourself room above the sample to capture the population mean. That's what the plus is for. And you give yourself room below the sample to capture the population mean, and that's what the minus is for. How much room? It depends on how confident you want to be. So if you want to be 90% confident, you take 1.65. That's the critical value. If you want to be 95% confident, use 1.96. If you want to be 99% confident, use 2.58. Where do these numbers come from? Let's take a look at the z-table. Let's go and find 1.65 in the z-table. We'll start with minus 1.65. I go to row minus 1.6, column 0.05, and I get about 5%. So about 5% of the time, I'm going to get a z-score less than 1.65. And then if I go to positive 1.65, row 1.6, column 0.05, about 5% of the time, I'll get a z-score higher than this. 5 plus 5 is 10. So 10% of the time, I'll get a z-score that's further away from 0 than minus 1.65 or positive 1.65. 90% of the time, I don't. That's the justification for the 90% confidence interval. What about 95? I use 1.96, row 1.9, column 0.06, and you can see this 0.975. 2.5% of the time, I'll get a z-score larger than 1.96. If I go to minus 1.96, row minus 1.9, column 0.06, that's this z-score right here. 2.5% of the time I'll get a z-score smaller than minus 1.96. 2.5 plus 2.5 is 5. 95% of the time I don't get a z-score that is smaller than minus 1.96 or greater than 1.96. And the thought is that, hey, this is the probability of getting a sample that is this distance from the mean. So 2.58 corresponds to 99. So if you want to be more confident, you give yourself more room to work with. Okay, so we draw the confidence interval around the sample mean. And let's say you sample 23 people about how much they studied for Econ 3402. And they say 35 minutes a semester, which is terrible. That's the sample mean. The standard deviation is 13.4 minutes. I can make a confidence interval that captures the true population mean X% of the time. I plug in the z-score. Let's say I want a 95% interval. I plug in a z-score of 1.96. I plug in the standard deviation for sigma. That's 13.4. I plug in the sample size of 23. That's right down here. I add to get the right portion. I subtract to get the left portion. That's my confidence interval. Now let's say I want to do another confidence interval. And this time I want to find the probability, I want to make a confidence interval associated with spending at Wendy's. And let's say I sample 45 UWG students. And the sample amount spent, 782. Standard deviation, 222. What does a 90% confidence interval look like? Sample mean is X bar. So that's 782. Standard deviation is sigma. That's 222. Sample size is 45. Or I'm sorry, that's n. That's 45. Confidence interval. Z-score for 90%, 1.65. I take the sample mean. I add the z-score times the standard deviation divided by the square root of the sample size. That's the right-hand side of the interval. So what about the left-hand side? I take the sample mean, I subtract the critical value times the standard deviation divided by the square root of the sample size. That's the left-hand side of the interval. Now Excel will do this for you. You can use confidence.norm. You use your alpha. Your alpha here, if you just click on it, alpha is how much probability you want left over. So you can do 0.1 for 90%, 0.05 for 95, and 0.01 for 99. The standard deviation is listed here. The sample size is listed here, and you hit enter. And you can see that this generates a margin of error. If I just take the sample mean and add the margin of error, I get something that is very similar to what I had before. The only difference is that there's a little bit of rounding that went on with 1.65. Excel doesn't round. And I can do the same thing to get the left-hand side. Alpha is 1 minus 0.9. So Excel automatically does this for us. Okay. Interpreting the confidence interval, the key point. I don't know what the population mean is. If I knew what it was, I would not need to sample. There are two possibilities. X% of the time, the population mean is within the confidence interval before I make the confidence interval. So once you make it, it's either in there or it's not in there. It's not like 10 is between 9 and 11 95% of the time. That's not how numbers work. But the point is that if I employ a process that generates intervals like 9 to 11, that process will find the population mean X% of the time. The 1 minus X% of the time, the population mean is not within the interval. And so the whole point of the interval is to pare down where I look for the population mean. Of course, the mean is some number, but maybe I can do better by being more precise about where to look. So it doesn't do us a lot of good to go to Chick-fil-A and say proudly to management, well, I know that families spend between $0 and $700 on dinner here. That's unhelpful. Of course, that is true. It's trivial. However, it might be more helpful to say I think families will spend between $28.57 and $32.48. That is a range in which you can make some decisions about future hours for your employees or how much to order, etc. A secondary purpose of the confidence interval is that frequently I have a strong opinion about what the population mean might be, and if it's not in the confidence interval, that's worrisome. And so that's an idea that we're going to leave off with.